So before we quantize the scalar field, let us review the quantization of a classical Hamiltonian system, a very simple system such as the simple harmonic oscillator. So remember the Hamiltonian for the simple harmonic oscillator. It has only one degree of freedom, so there is a one-dimensional momentum term and then a kinetic energy term, and then there's a potential term. And both of these terms are quadratic. So the Hamiltonian of a scalar field is similar to this Hamiltonian in the sense that the Hamiltonian of the scalar field is also quadratic in the canonical momentum as well as the field itself. So in classical mechanics, what we do is that we impose a Poisson bracket relationship between the fundamental coordinate and its conjugate momentum. So in classical mechanics, we expect this. So this is the Poisson bracket. So this is going to be 1. And if our system has more than 1 degree of freedom, then the Poisson bracket just becomes, so this is J. So this is what it becomes in classical mechanics. Now, the quantization of a classical mechanical system involves in replacing this Poisson bracket by 1 over I h bar times the commutator, as well as replacing the the fundamental variable by their operator counterparts. We're not going to use the hats for the operator. So if you do this, then for the for this system for which the this is the Poisson bracket, the fundamental quantum commutation relationships become the commutator of xi and pj is I h bar delta ij. So for the simple harmonic oscillator, this is also true. Well, what is true is the commutator of x and p is I of h bar. But also in the simple harmonic oscillator, what we did is that we introduced the annihilation operator and the creation operator, and they were given by this expression. The precise form doesn't matter, but it was what was important is that they were a complex linear combination of the position operator and the momentum operator, and their complex and their Hermitian conjugate, which had a minus sign. And then, this commutation relationship, along with the trivial ones, became, for the harmonic oscillator, the commutation relationship, the commutator between A and A dagger is 1, as well as the commutator of A with itself is 0, and the commutator of A dagger with itself is also 0. And remember that the Hamiltonian can then be expressed as a bilinear of A plus half times h bar omega, where A dagger A, often written as n, is the number operator, and its eigenvalues consist of 0, 1, 2, 3, 4, ... That is, its eigenvalues are positive integers. So what this means is that, the eigenvalues of the energy, the Hamiltonian, are given by half h bar omega, 3 halves h bar omega, 5 halves h bar omega, so on and so forth. And what is important is that the ground state has a non-zero energy of half h bar omega.